All right. So right now we are on standby for the stream. So actually, Timo, if you can share the link. Um, yeah. All right. So right now we're just right now. All right. Hello, everyone. Welcome back to the ClusterDuck stream. I am Nick. I'm here with Timo and also our guest, Kahlil. Kahlil will be doing a presentation today about bloom filters. He's been doing a lot of work on building a custom bloom filter to work for the CDP, and so he's really excited to show what he's been working on, explaining how going more in depth on how a bloom filter works, as well as also how we calculate false positives and what that really means. Um, and then also we'll go into a little bit of the work that he has done so far. So Khalil, why don't you, before you jump in, maybe you want to just talk a little bit about your stuff, yourself, and what what you've been doing.
Okay, hi. So, yeah, I'm currently a PhD student in computer science at Columbia University. Just finishing up my first year, working on a few projects and stuff like that. But yeah, so been getting into bloom filters a bit lately. So yeah, pretty excited to, I guess, talk about them and explain the background and yeah, see how everything works.
Yeah, thank
So,
you. Sorry to
yeah.
interrupt your growth, but for everyone joining back, we have three previous streams talking about Bloom filters, so you can always go back and watch at those. We use the Bloom filter for network routing. That's all explained in the previous videos. This video is going to be more in depth. What is a Bloom filter and how we're going to like how we are going to decide which version of Bloom filter we implement. So um, everybody just it's going to be pretty intense deep dive, but I think everybody is waiting for this. So thanks everyone, and I will give you the word. And excited to see this.
Take it away, Khalil.
All right, great. I'll start presenting my screen now, I guess. And I'm assuming everybody can see the slides. Just
Yeah.
well, if not, okay, great. So yeah, talk about bloom filters. So yeah, what is a bloom filter? So basically, in a sentence, I would say a bloom filter is just a data structure that can be used to efficiently store data. And by efficiently, specifically here, bloom filters. What's nice about them is that they don't take up a lot of space or memory in your computer. You can store a certain amount of data with less space than similar data structures. So that's very nice. And the way it accomplishes this is because it's probabilistic in nature. So it takes advantage of randomness, and through taking advantage of randomness, we get efficient, less space taking up data storage. So in a nutshell, that's what bloom filters are, and I'm about to explain everything about how they work. So again, so you might already know what we use bloom filters for, but you can imagine you have like just a node or something that's receiving an incoming stream of messages, right? And for the purposes of this discussion, we can consider a message a string of alphanumeric characters. So we're at a node and we receive a string of messages, and we are considering the set of messages we've seen so far. So right here, we can just like imagine there's a collection of messages we receive, and we record the messages we've seen so far. Although it's important, it's a set. So if we see a duplicate message, we don't record it twice. We just, these are any messages we've seen at least once. So we have that, and now imagine we receive a new message, right? Like a certain string, just whatever, AX7135, whatsoever. And the question that the Bloom filter is going to answer is, it's used to detect duplicates. It asks, have we seen this message before? Is this new message in our set of messages that we have previously seen? So that's what a Bloom filter is going to answer for us. And the thing is that with the Bloom filter is it answers that question for us, but this goes back to the randomness again. It answers this question for us with a very low false positive rate. And what this means is that sometimes, but ideally, if you design it well, this shouldn't happen often, but sometimes there's a possibility that the Bloom filter is going to actually give you the wrong answer. It's going to tell you that we've seen the message before when we actually have never seen the message before, right? And this probability of this false positive, that's essentially the trade-off we accept in, because the Bloom filter is so space efficient, but we have this little small chance of false positives. And that's a fundamental engineering trade-off with Bloom filters. So yeah, let's get into the details of how they actually work. So a Bloom filter is, there are two main parameters with a Bloom filter, M and K, which you might see a lot in the literature. So a Bloom filter of size M is just an array of just M bits, or rather M buckets of bits. And all of them are initially set to 0, like just drawn here, a simple array of bits, all drawn to 0. And in addition to this array, we also have K hash functions. Here I've denoted H1, H2, all the way up to HK. So your array of size M and your K hash functions, that's basically your Bloom filter. And so, okay, so just actually a real quick little background on hash functions and how they work. So how hash functions work is basically they take an input message of any length and they output values in a restricted range. So for the case of a Bloom filter, our hash function is going to take in a message, whatever, it can be however long as we want it. But what the hash function does is it outputs a value in the range of our Bloom filter. In the case of our Bloom filter, if it's size M, it's going to output a value, a range 1 to M. And I've just, drawn some examples here of how that might work. We get a message AX7135, and we apply a hash function to it. It outputs 7. Another message might output 3. Another message might output 11. So that's a basic idea of a hash function. You've probably heard them before. But here's the key thing with hash functions. So there are actually plenty of ways to implement a hash function, right? But if you want the ideal hash function, a good hash function, this notion of a good hash functions are essentially appropriately random. So if we have a good hash function, if we give it random input values, its output value should be uniformly spread across its output range, right? It shouldn't come up 7 much more often than it comes up 3. It should be spread across 1 to M pretty evenly. So if we have a good hash function, good hash functions are easy to find. Pretty much all the popular ones you've heard of are good enough. That's a property of good hash functions. So again, Bloom filter, just M bits and K hash functions. And like I just actually alluded to, it's very important that all of our K hash functions are independent. All that it means is, in layman's, well, precisely what it means is that our hash functions should have no correlation between their outputs. What it means is basically if you give it the same input, right, different hash functions should give you different outputs, as I've just denoted here, right? If we have K hash functions, if we give it the same string, we should get K different numbers. We shouldn't get the same numbers. So if we have those two ingredients, the array and these independent hash functions, we have our Bloom filter. So how does the actual algorithm of the Bloom filter work? How does it store these messages? So let's walk through an actual example. So here let's assume we have a Bloom filter of size 20 and 2 hash functions. So M equals 20 and k equals 2. So when our Bloom filter gets a new message, it's pretty simple. It just applies these k hash functions to this message. So imagine we have Bloom filter, a message AX7135 comes in. It applies our k equals 2 hash functions. We get, ideally, 2 different numbers in the range of 1 to 20. Here, I just, for example, just arbitrary example, let's say it's 7 and 1. And all we do is we set those corresponding bits in our array. So as you can see below, the Bloom filter bits 1 and 7 are set to 1. And we just repeat this process over and over as we get new messages. So every incoming message comes in, we apply it to these 2 hash functions. Ideally, if it's a different message, our hash functions are independent enough. We're probably going to get different bits to set. So we set them, and eventually this repeats and repeats. And as you might imagine, our Bloom filter begins to fill up with ones. And although a key fact to note is that as we add a new message to the Bloom filter, if we ever find ourselves previously setting an unset bit to 1, we instantly know that we've never seen this message before. Why is that? Well, because if we saw it before, we already would have had set the bit to 1 before. So, and by the way, so a Bloom filter will, with no error, with 100% certainty, can tell you that, hey, we get a message, we've never seen it before. That's a good thing. But you might anticipate, but what's the downside? The downside is what happens if we get a new message, apply those k hash functions, but all those bits are already set to 1. So for example, we get a new message, new message, 1, 2, 3. And the first one hashed to 1, the second one hashed to 7. As you imagine, this will eventually happen, right? Because eventually the Bloom filter gets filled up enough. At some point, this is going to happen. So that's precisely the problem of the false positive. So that's the Bloom filter telling us incorrectly that when we see a brand new message that it's a duplicate message. All right, so there we go. That's in a nutshell the fundamental trade-off. We get this nice space-saving algorithm that takes advantage of our hash functions for randomness, but these collisions can sometimes happen. Although through good design, and that's ideally, this false positive probability can be made acceptably small. What does acceptably mean? Well, it depends on your application, but we can precisely quantify exactly what this false positive probability will be in terms of parameters of our Bloom filter. So let's do that. So yes, so again, yes, we can. So how do we calculate the probability of these collisions, these false positives? Well, we can precisely express it in terms of 3 parameters m, k, and n. So m, if you recall, is the size of the Bloom filter, the number of buckets we have to put bits in. K is the number of hash functions, all independent hash functions that we choose. And n is the actual number of messages that the Bloom filter that we've added to the Bloom filter. And so let's just go through the derivation of what's the formula for the false positive probability. So just to start, just imagine we just have an empty Bloom filter size m. So empty Bloom filter, m bits. We get a new message. And now just consider just any single arbitrary random bit in the filter. Now, again, if we have our nice, good independent hash functions, its hash, if the hash function on the message should be nice and evenly spread out between all m of those values. So every individual bit should have an even 1 over m probability of being set to 1. So if we have a size 100 Bloom filter, every bit has a 1 in 100 chance of being set to 1 by a single application of a hash function to a single message. So what's the probability of remaining unset? Well, the probability of something happening is p. The probability of it not happening is 1 minus p. So the probability of a single bit remaining unset after a hash function is applied to the message is 1 minus 1 over m. All right, that's great. But with each message, remember, we don't just apply one hash function, we apply k hash functions to it. So, and since we're assuming all k hash functions are independent, we apply k times that probability. So the probability of it remaining 0 after adding a single new message and hashing with k hash function is that quantity 1 minus 1 over m raised to the kth power. So that's after we've just added a single message, hashed it with k things. That's the probability of a single bit remaining 0. But now, imagine we add n messages. Well, similarly, the pattern you can imagine repeats. You just do the same thing, but now do it n times. So you raise that previous quantity to the n, and 1 minus 1 over n to the kn. That's after we've added n messages to the Bloom filter. Any random arbitrary bit still remains unset. So it's been untouched by the algorithm so far. So so what's the probability of being at 1? The probability of being at any point touched by the algorithm so far is 1 minus that. And then finally, for the final thing, so what have we just calculated? We've just calculated n messages. We've added n messages to our Bloom filter. What's the probability any old bit, any other random bit in the Bloom filter has been set to 1? Now, now if we get a false positive, remember, how does that happen? That happens if we have a full collision. That happens if we see a completely new message and every single bit in that message has been set to 1, all k of them. So once more, to get our final probability, the probability that we have a collision on every single one of the k bits when we see a new message in our Bloom filter after having added n messages is this quantity here at the end, false positive probability, this thing here. And again, depends on m, n, and k. And actually, yeah, let's look at a little bit about the dependency on m, n, and k. So the first thing to note is as m grows larger, so m, remember the size of your Bloom filter, as m grows larger, the false positive probability actually goes to 0, which makes sense. As you have a larger and larger Bloom filter, less and less chance of collisions. Makes sense. But conversely, as n grows larger, so as you add more and more messages to your Bloom filter, the false positive probability of collisions goes up and up and up and up and up. So that's actually what this equation says. So it's a sanity check. This equation totally makes sense. So, I mean, in layman's terms, the bigger the Bloom filter, the emptier it is, the smaller chance of error. Conversely, the smaller it is or the more full it is, the bigger chance of error. And although this formula here is actually precise as long as, once again, we assume our k hash functions, there's 0 correlation between the hash functions. They're perfectly independent. But even if not, because in reality, you're probably not going to have 0 correlation. But as long as m is much bigger than k, you shouldn't have to worry much. And this formula is very accurate enough. So, okay, so actually, there's a problem that comes up with a Bloom filter. So it's great. We have a nice space-efficient way of testing for duplicate messages with a very low chance of error if you choose your parameters right. But there's a problem deleting, removing items for a Bloom filter. So, I mean, you should already be convinced that a Bloom filter can tell us, if we've never seen, if a message we've seen is brand new with, 100% accuracy. But what it can't do is tell us what the actual content of the messages we just added are. I mean, just look at it. We just added a bunch of strings. We have a bunch of bits. It doesn't tell us anything about what strings we've added. And in fact, there's not enough information in there for it to fully be recovered. So we can't do that. And that's expected. That's actually a consequence of the space-saving property of the Bloom filter. So that's a drawback of this. When our Bloom filter gets too full, can't delete individual messages to free up space. We essentially, actually, the only thing we can do is delete the entire thing. We can't delete the last message. We can't delete the last 2. We have to delete every single thing in the Bloom filter and start all over. So that's unfortunate. Is there a way to get around this? Well, kind of. So one idea is you could use 2 Bloom filters, essentially. So basically, you have 2 Bloom filters here. I have denoted them A and B. So at first, the algorithm starts as normal. Just add messages to A as normal, and then when A gets sufficiently full, by sufficient it means whenever you choose, it's a parameter you can choose or whatever. Instead of deleting everything and starting all over, instead we don't delete A. we keep all the information that's inside of A and instead switch to recording new information in B. So when we get new messages, we still check A to see if the messages were, if we've already seen them before. But if it's a new message, we continue recording it in B. So as you can see here, like we get a new incoming message and bits 1 and 7 are B is set up. And this continues on. And as you can imagine, when B gets sufficiently full, that is when we finally wipe out A and start over, but we haven't lost everything because we still have everything from B we've recorded up until this point. So that kind of tells us what this gains. Instead of periodically forgetting all the messages we've seen so far, and once the bloom filter gets too full and having to start over again, we've given ourselves a running window of messages essentially. So eventually we forget messages, but not all of them at once. So that's kind of a way to get around the limitation of not being able to remove items from the bloom filter. And okay, and then one final thing. This is just a nice little trick. So if we have a bloom filter, and again with a certain size with k hash functions, actually we might not need k hash functions. If we have a really, really good hash function that's big enough, we might not need k hash functions. Instead, we can use one hash function and split it into k parts, essentially, as so. So imagine we have a bloom filter of size 2 to the m, and our parameter, we parameterize it with k hash functions. Instead, we can take one hash function, as long as the hash function has m times k bits of output, that is, it returns values in the range of 1 to 2 to the raised to the mk power. We just hash our message on that. We have our mk bits of output. We take the first m bits, that's our first hash function. Take the next m bits, that's our next hash function, and so on. And then we get k different hash functions for free, essentially. It's k for 1. Nice deal. And again, so as long as the hash function is good enough, you should be able to do this with pretty high confidence that it's acceptably random. And yeah, that is all I have for this presentation on bloom filters. I guess if we have questions or
that was amazing. I do have a couple questions. I think you explained it very well. There's a big question I have for you. I don't know if you've done any research, but how do you decide M? Is there a way to? Is it based on literally the physical machine you're running it on, or is there another way to determine M?
Yep, it's based on the application. So all of the parameters, yes, the physical machine you're going on, the amount of memory constraints you have, what you consider acceptable tolerances for probability. So yeah, that's just a pure engineering question. Depending on the application, that's how you decide your M. It's just this, the analysis I gave you just gives you the theoretical, the justification for this is why we chose this.
And yeah, so you have to keep in mind that if you decide M, you're basically deciding double M because if you're running 2 bloom filters, you cannot go with maximum M. You're wanting to split that in half so you can use 2. Do people use triple bloom filters, or is it kind of common to use 2 and switch over when the one is full?
I am not sure. In practice, I'm not sure what's the most common. As far as I mean, you could absolutely use an amount of bloom filters. It seems like my impression is more than double should be sufficient enough for, I guess, most applications. But you can use as many as you want. It works just fine. Yeah, because it's just memory constraints.
That's maybe for someone that the next phase I think for us is going to be we know I now honestly have a much better understanding of how bloom filters work. It's, we have to implement this to an actual application thing, which is our data protocol. I think that's when you have to make all these decisions on, how big is M going to be while we have different boards we're running on. We have different machines we're going to be using this for. There's a lot of variables we can decide, but I think how you describe this, where you have the double bloom filter, you switch it over, and using all the hash functions as well. That's all based on the actual implementation of the bloom filter itself. But yeah, I thought it was great to hear it from you, who actually how you described it. That was perfect.
Yeah, and it's very much comes down to like what is the acceptable probability, right? And so,
Yes.
and me something also me to clarify, may clearly want to clarify on if let's say go back to that if you go back to that one example where you had the first one where you had the first hash function said came out with 1 and the second one came out with 7. Well, what would be the situation if the first one came out with a 2 and the second one came out with a 1? 1 has already been filled, but
Okay,
but
so
the other one has not. So what happens there?
So that's what happens there is the algorithm works perfectly just fine. You essentially identified the key to the space saving part of the Bloom filter. So as long as there's not a full collision, the algorithm works perfectly fine. So every single bit can collide except for the last one, no problem. It's when literally every bit collides, that's your false positive.
Mm-hmm.
So,
And that's why having more hash functions, you can extend that, and
Yep.
But also that comes at the cost of m, because you're now storing more values because more function. It makes sense how there are more hash functions. You're storing more values per message, and so if you had infinite storage space, you could have infinite m, and you'd have a probability of 0.
Yeah,
right?
I mean, if you have infinite storage space, why are we even using a Bloom filter, right?
Yeah, exactly. Yeah, so so me, I don't know, do you want to go into a little bit of your what you have been working on so far? Actually, me, one other thing I wanted to mention before even talking about that is Kahlil has been also working with another student on figuring out. So one of the things that you need to figure out is like what is the acceptable probability, and that also comes into how long do you need the Bloom filter to live, right? So you don't want to prematurely. So we don't want the Bloom filters to fill up too quickly, where there's a chance that a message can come back. Let's say it comes back half an hour later or something like this, and then you end up starting the whole cycle again, and then you're just infinitely sending the same message over and over again when it should be suppressed. And so Kahlil is working with another student on coming up with a simulation, and I've looked at a little preview of it, and I think it'll be once that is done, I think it'll be a really great representation of how watching the Bloom filter switch and how that process works. I think will be really interesting. I don't know if you want to talk a little bit more about that, or want to jump into a little bit of the code.
Oh, are you asking me?
Yeah. I don't know if you want to talk more about that simulation that you've been working on, or if you want to just look at a little bit of the code that you have so far.
So you can certainly look at the code. As far as the simulation, that problem you said, I just started looking at it today. I believe Lockman has done a little bit more on the simulation. He could probably tell you more about that. But
yeah, because that's something we have to keep in mind is if a duck would reboot, automatically a Bloom filter would be empty, which would be fine, I guess, because it never happens where, packets go so quickly back when it reboots, it will receive it again. I think that time goes too quickly, but it's always, they're always more of the.
Here's the other thing though, Timo, is that, as Kahlil was saying, is it's extremely space efficient. So this is something that is because we're doing is storing ones and zeros, right? And we could store that very easily in the EEPROM. So even though it reboots, it can be saved on the internal memory. We can actually write that in because the only when we reboot, the only thing it'll be written is the flash. But we could be able to, because it is so space efficient. Because all it is just bits, and we just need to know if they're on or off. We can very efficiently, even if the Bloom filter is relatively large, I guess we should be able to store them. So, but that is a good point to make sure to put that.
Just one other point. If you have one duck that reboots, and you lose the bloom filter, all that happens is that duck will be forwarding messages that it didn't necessarily have to forward. And if you have one duck in your network doing this extra forwarding, that in itself isn't a huge problem, right? If all the ducks simultaneously reboot, then you're sort of starting from scratch. But one duck really wouldn't be a huge problem from a performance standpoint.
That's a good point. That duck would just relay it again, which is honestly not a big problem if it does it again, because all the other ducks have already seen it. And it almost never, I feel like the data goes so fast as well. Whenever it reboots, it would never have the time to come back to it before it actually rebooted again. So
we should be able to calculate these parameters, and like Dan said, is that it will, that it probably will not be the biggest issue. That makes a lot of sense.
Also, one thing that wasn't mentioned in the presentation is that the different ducks would be using different hash functions, or there'd be a pseudo-random number associated with each duck that would be incorporated into the hash function. So even if one duck has a false positive on two messages, bloom filter collision, and it happens to continue to forward that message, the other ducks, it's very unlikely, since the whole thing is randomized, that they would have the same collision. And so one duck might be replicating a certain message, whereas the others would know to quash it.
And I think that's the strength of the mesh network is, again, the more ducks we're adding to this network, the less of a chance that actual packets are being repeated, because every duck has a different outcome. If every duck would do exactly the same thing, you can if it might have happened, a packet gets forwarded twice, every duck will do the same. But as a very good mention, if every duck's doing something different, the actual possibility for a duck to end up at the Papa duck duplicate, I think is going to be super small, which is great. So Kahlil, did you do any research on which hash functions and how we built them into like our code? I think you've done some of it. Curious to know if you can share anything about the type of hash functions, because I don't know anything about it. So I'm curious to hear if you can share anything.
As far as what do you mean hash functions you have in your code? I don't know anything about hash functions you're currently using or anything like that. But as far as good hash functions to use, I mean, most of the, big name ones are really good enough. I mean, the choosing of the right hash function, that's not the hard problem or anything. For your purposes, most commercial hash functions probably perform acceptably well. Like I don't know if you've heard the SHA. Well, that's a big popular one. That one, the bit fields have more than enough, or more than little enough correlation between its outputs. I believe to you can trust so you can trust the formulas here, as long as again, M is bigger than K, obviously.
That's great. Yeah. So Nick, I think this gave us a better insight of how we can leverage this and why we set certain parameters. So that was the big problem in the last week's stream, is we used default parameters from the example because we were like, oh, I don't know what these values mean. I think we can start thinking about how do we set M based on the board we're using, based on maybe the future of because we're going to be compatible with different physical microcontrollers. We're going to be compatible with different simulation software. So I feel like there's always different option to set M to a different size.
I would say that is 100% depends on your application. So the answer to that would be, you have to answer exactly the questions you brought up. Exactly. Yeah.
And I think that's why the simulation that you guys are working on will really help figure out, well, what, how do you turn those dials? Which dial do you need to turn to make it work? At least how long do you need to keep those bloom filters for a network of a certain size, right? It's going to be different between a network of 100 versus 10,000. So that's why having a simulation will really help us figure out what we'll need to do.
Great.
Yeah.
Nick, is there anything else you want to dive into? Want to discuss?
Well, I know clearly it's a little bit still in a work in progress, but I think
I mean,
I think
I'd be happy
everyone,
to
yeah, just to kind of like show it
Yeah.
and kind of go over it since we have a little bit of time.
Yeah, sure.
Because
Give you a,
the rest of our community will be interested to see how you implemented it over the last streams. We were using a library that someone had made, but what Kahlil has been working on is much more tailored to what to the CDP's needs. We don't may need something that was so was maybe a little bit more complicated, but here is much more tied to what our needs. So if you want to just bring that up.
Yeah. Okay. Let me share my screen again real quick. And yeah, so I implemented this about 100 so lines of C. Okay, I'm assuming everybody can see the code on my screen right now.
Yes. Perfect.
And
Yeah, if you can
okay.
actually make it bigger and then zoom in. That's good. Yeah, perfect. Yeah, I just saw on the stream it when after it renders, it's sometimes a little bit hard to see.
Yeah.
But this is perfect.
Yeah. Yeah, so this is basic implementation of the bloom filter in C, and I believe I also, yes, added so this is the two bloom filters switching back and forth between the rest of them. And again, it's only about 150 lines, so the implementation of the actual algorithm is not that complicated. The key here is to, get a good hash function. This is a hash function implemented in C. I literally grabbed off the internet, but it should not be that hard to find one good enough for your purposes. And here, okay, it takes in as command line parameters M and K. Again, M is the size of the bloom filter. K is the number of hash functions we want. And just allocate memory for two bloom filters. Again, we're going to switch back and forth between the two. So what I allocate M slots of M bytes of memory for each bloom filter.
Wait, can you go back and highlight that part? Just kind of just help people see what if you just highlight the parts that you're talking about, so it makes it a little easier for people to follow.
All this is just So all this is just allocating M bytes of memory for each bloom filter, and then initially filling them with zeros. And then just all this is just seeding the hash function. So this is just making sure our hash functions work. And okay, so the way this particular program works, just for I developed, again, this was quick and dirty. I have the user input 1,024 characters on the line, and it's just an infinite loop, and it's just this program just prints out if the string is in the filter or not. So okay, and this is the core of the algorithm. First of all, this is us generating our K indices for the string. So I just apply the hash function K times, and you see for loop goes up to K. I'm just applying the hash function K times and assigning it index in the range of 1 to M. And this is a little bit to make sure we have a unique index each time, and this will slightly mess with the true independence of the probability, but as long as, again, M is much bigger than K, it's not something we should have to worry about. And this is just setting the index. So all this is just generating the hash indices and then setting the corresponding index in the bloom filter. And you might see these some variables, filter collisions. These are just tracking to see if there are false positives. It tells us if we have a collision or not. So, and again, interesting enough, at this point in the code, even before the algorithm's completely finished, if we ever find ourselves inside this int statement, we can instantly return, hey, we know a new string. So as far as time efficiency goes, that's just one little nice quirk of this algorithm. But again, so basically, so now it tests for the collision. So again, if all of our bits were, if any of the bits were 0, we know for certain that we have a new string. We've never screened before. With 100% accuracy, it will identify true negatives, our bloom filter, remember.
So Kahlil,
However, yes?
Quick question here. Each bloom filter index is currently a byte.
Okay. Yes. For the purposes of this program, yes. So each bucket is a byte big. It doesn't have to be a byte big. You could implement it to make it a bit big. But yeah, for this little program, yes, each bucket representing a bit is a byte big. Correct.
Right. So we'll eventually need to reduce that to a bit.
Yes. Yes. Correct.
Okay.
Yes. So Okay. So if we haven't seen the string, identify true negative. But if we have seen the string, we know I say possibly because it might be a false positive. So that's all. Just it just prints out whether we might have a false positive or not. And then finally, this implements the little switching back and forth part. Basically, I have a parameter. This parameter says, okay, this is messages are full enough. And once we've hit this parameter, we just freeze the filter, make the other filter active. And that's all this is. And that's about it. And that's just the hash function. Again, just grabbed from the internet. So 150 lines, just a quick and dirty implementation of a bloom filter. As said before, there are plenty. You can probably identify yourself of ways this could be made more efficient. But this just gives you just a quick and dirty example of how implementing a bloom filter might actually go about in code. So, yes. Any other questions?
Yeah, no, that's great. No, I'm, I think even though this maybe doesn't have the bits yet, but it does show how it's supposed to work, and the 1 and 0s, and so I think it'll make it very easy to understand. So, yeah, no, I think it's really awesome. I'm very excited for these bloom filters. I know our community is as well, because it'll free up so much space for us, and we'll be able to do a lot more with the network than we have down. So now we just kind of need to take it to the next step, and then also figure out what is the acceptable false positive. I mean, I don't know, that was actually a question. What's an acceptable false positive rate? Like, so what is like maybe a target? I mean, I know it's like 0% is is the ideal, but what's the lowest that you like, where every 1 in 100, or what is like, when is it acceptable? Like, what kind of, where do we get that?
As far as answering that question is, well, I guess, depending on the application, I guess the question you would ask is, like, I don't know, like, how long, what time scale, I guess, would you think like a false positive would be acceptable? Do you want one false positive a day, one false positive a month, one false positive a year, depending on, like, I don't know, depending on whatever your application it is, maybe that makes sense. I would say start from there, then start from how many messages you get in a certain amount of time, and from there, I would say that's how you might want to have a start at estimating what your false positive rate is, because maybe 1 in 100 would work if you only get like a message every week, or which would not work so well if you get a message every second. You know what I'm saying?
Yeah, exactly. Let's see, got another comment here from Amir. I think that this may be dependent on the size of the duck cluster and the frequency of messages relayed by the mama duck.
Exactly. Yeah.
Mm-hmm.
Well, again, if you remember that the likelihood of false positives is independent of the different ducks. So even if you had a high false positive rate of like 10%, again, that would only be 1 or 2 ducks making the mistake of retransmitting the message. It would still probably die out, and a false positive rate of that high is really trivial. I mean, you can have a very small bloom filter. So I think, I think what we're going to find is this will be pretty easy to overcome with, not taking up too much space or effort.
Mm-hmm. Yeah, and like Dan mentioned before, if one duck makes a mistake, it's not like the whole network is making the mistake at the same time. It's going to be one duck making an isolated incident. So that's also, I guess, another layer of the probability of yes, this is the let's say like it's 1 in 2 million. Let's just say that as 1 in 2 million that one duck will make a mistake. But you also have other, since it's a mesh network, you're going to have other ducks in the area that will be able to make the right decision because they'll be on the other side of that 1 out of 2 million chance. So it won't be it won't be disastrous if we get a false positive. So even if it was like even lower, like 1 in 2,000 or something like this. So what's more important though is understanding the time to live a message in a network. And then also Amir has made another comment, and we can also configure the PapaDuck Bloom filter to be more resilient to false positives, so ultimately filtering out duplicates at the gate. So one of the things that happen in a mesh network, we're creating a lot of duplicate messages, right? Because it's a broadcast, and so when two ducks receive, like the messages that are created, it's 2 to the n. For in a mesh network where you are, n is the number of devices you have in a network because it propagates out and every single device is making its own message. And so you'll have a lot of duplicates. And so this is also would be using a Bloom filter would make this a really quick way to filter out all those duplicates, and actually will help, for us. If we're also from a practical, like when we were doing deployment in Puerto Rico, where we would get 10 duplicates and we would be sending that to the cloud. And if we're able to filter that out very quickly at the PapaDuck level, that saves money in the sense because if we get charged for every transaction we send over the internet. So it's also not only a protocol saving, it also makes it more efficient for us cost wise. So yeah, really amazing stuff. Are there any other questions that anyone wants to ask while we have Kahlil on the line here? Because I think other than that, I mean, this was a really awesome presentation, much more in depth and much more understandable than my ramblings was a couple of weeks ago. So really appreciate how you went in depth.
Thank you.
And I think it's actually better than some of the explanations I found online. So I think this is a really well put together presentation. So really looking forward to.
I think this is a great kind of milestone for us, talking about this for over a year and a half. Finally, kind of like, oh, this is how it should work, and this is why we use certain parameters. So, thank you for clarifying. I think it really helped us and also hopefully the community. And I'm excited to start implementing and hopefully getting our first tests going and collaborate more with everyone here and on the stream. So, thank you for that, for your time. Same for Dan, your input. And I think we will have some more updates very soon with like our first ever testing. So that sounds great.
Yeah, and also we'll be using this video as part of our design documentation. So, like I was mentioning before, will be helpful for community members down the line when they see, okay, we have this Bloom filter. How does it actually work, and why are they using this thing? So we'll be able to reference this stream. So, so really awesome job. Thank you for joining us on our stream today. Really awesome job. Total natural on the stream. Just full of energy and just like going ham. So love it. So thank you very much. And thank you everyone for watching, and we'll see you next week.
All right, thanks
Thanks
guys.
everyone.
Yeah.